Okay, good morning, everyone. We have another subcafe session, and our speaker today is Gailliot. He is a fourth-year PhD student. He is originally from Wilmington, Ohio, and he's a Sandia Global Security Scholar Research Fellow at Sandia National Laboratory. That is very cool. His research interests include statistical networks and Bayesian statistics for nuclear security, that he's doing at Sandia Labs. And let's welcome our speaker.
All right. I see you checked my LinkedIn. Okay, so I'm going to be presenting my work that I've done under the supervision of my advisor, Dr. Guhani Yogi, and alongside our collaborator, Dr. Roger Peng from the University of Texas at Austin. And already on the first slide, there's a lot of words here, but don't worry, I'm going to explain them. I'm going to read the title first. So it's Data Sketching and Stacking, a confluence of two strategies for predictive inference in Gaussian process regressions with high dimensional features. So what are we talking about? We're talking about Gaussian process regression in high dimensions. And we're solving it not in a typical way that's already been done using something like ARD kernels. We're using two strategies, data sketching, which if you came to Jacob's talk a couple of weeks ago, you've already heard of, and stacking, which is a method of model averaging. Okay. So I'm going to start by introducing the problem. Specifically, I'm going to introduce the real data application that motivates this approach. And then I'm also going to discuss a simulation example that I'm going to be using throughout the talk. And then I will move into talking about sketch Gaussian process regression, and then the model averaging approach. And then I will show the whole picture, and then I will show you the results. So why are we working on this in the first place? The real data problem that we're trying to solve is, can we use remote sensing satellite data to predict air quality? The bottom picture down here, the one on the top, is the air quality, like PM 2.5. It tells you how much particulate matter of a certain size is in the atmosphere in Las Vegas from 2019 to 2023. The bottom plot is the logged and centered data, which is what we actually use in our analysis. This quote here is from my paper, but I didn't write it. My collaborator wrote it, so I thought it would be okay to use it. And it's an important problem because the combination of high resolution spatial and temporal coverage from satellite images with novel statistical prediction approaches has the potential to dramatically increase the monitoring of outdoor air pollution and its subsequent health effects. So the idea we're building towards is, can we use sparse air quality monitor data from cities and other places and kind of build a map of air quality across the whole US or something like this? So the response looks like this. It's a scalar response for every day. And the covariate information is 4 images. These 4 images are of the same place at the same time, and they're in different light bandwidths. So you have red, near infrared, blue, and green. And all of these images are of the Las Vegas region. So statistically speaking, we can write this problem down as a regression problem. We want to predict air quality, QT, given multi-band satellite image data, which I've called this MathCal X, and this is kind of a collection of the 4 bandwidths. Any kind of statistical regression approach you take is going to be solving this problem. If QT is equal to some function of, I'm kind of abusing notation, but the collection of the images plus some noise. Depending on the approach you take, the inputs X could either be the images themselves, like if you're doing a convolutional neural network, or 4 high-dimensional vectors, or 1 really big high-dimensional vector. But regardless of the approach, the information is always the same. It's the smoothly varying images, which I show here. And that's really the key that allows us to use Gaussian process regression. So for a GPU regression, XT is going to take the form, if we just naively blow the images up into big vectors and then stack them all together. It's 1 really big vector, which has dimension, if you don't do any screening or anything, it's like 65,000 big vector. But the images themselves have an inherent dimension, which is really small, right? So I'm gonna go back. All right, if you look at these, they're kind of topographic maps. They're smoothly varying surfaces. Even when they're blown up into huge vectors, they're still containing that information. So we estimate the inherent dimension using the R package intrinsic, which has these methods that I don't go into here, but I cite if you're interested. And the inherent dimension is like 1.5 for each of the images. Go ahead. Yeah, P1 and P2 are like the dimensions of the images. Right, so it's like this is P1, this is P2. It's like 128 squared. That there's 4 of them, yeah. Go ahead.
About the color on each of it, so there's not, what is like 3 channel in each pixel, or there's like.
So each of these is just one channel. The color on the image is the value,
Oh, you just. delete
the intensity.
image map.
Yeah, and these are all like referenced to be on the same scale. But they're all, it's just one number, right? So instead of it being RGB, like usual, our images are 4, right? So RGB and then near infrared. And then I split them across and showed them all here.
X is like a 4 slice of a pencil.
So yeah, I'm X here is, I'm just kind of being general, right? This is whatever regression technique you're using. X is just representing these 4 images. It doesn't have to be a tensor, right? In my GP regression thing, I'm doing the naive thing where I turn all of them into vectors and then put them together, which is, so this is, go ahead. It's just a scalar. It's,
Just one.
yeah, it's just these responses, like these values. Okay. So X appears large, but it has a small inherent dimension. Even when you stack them all together, the inherent dimension is still small. It's just 4 images. And then here's the first important result that lets us use Gaussian process regression, which states something like GP regression is able to make high quality predictions for data with a low inherent dimension, even when it comes to you, it looks like it's high dimensional data. And this is a pretty technical result that is actually having to do more with the manifold structure in the data. But here's another kind of statement of what we're doing. I'm going to present a method which draws computationally efficient predictive inference from Gaussian process regressions for large number of features when the response is conditionally independent of the features given the projection to a noisy low dimensional manifold. I've been trying to figure out how I'm supposed to show like mathematically what all of this means, but it got pretty technical. So really like the intuition is that the data is really this low dimensional thing, but it's coming to you in a high dimensional form. So instead of dealing with the real data for most of this talk, I'm going to be talking about this kind of canonical manifold regression simulation example. So we have our response here. This is scalar response versus X2, one of the features. And it looks like this, right? And within the features, there's a sort of structure. So this is X3 and X1, 2 of the features plotted against each other. And they have this sort of shape. This is where the Swiss roll name comes from. But all of both Y itself, the response, and the features are all generated according to some other thing that we don't have access to. So how is the Swiss roll data generated? First, you sample these manifold coordinates, T and H, and then you construct both X and Y referring to T and H. But when you do the regression, right, you want to predict Y given X. You don't have access to T and H. So the manifold thing is coming through, the manifold being T and H is coming through the relationship between Y and X. And that's what we're going to utilize to make good predictions. And in this simulation, always I can pump up the dimension of the simulation study just by including extra noise. So there's 3 features that are functions of the manifolds coordinates, and then the rest of them are just white noise. So we can apply, go ahead.
like X1, X2, X3, and X4. Each one only has either T or H, no overlap.
Yes. I guess in principle, I could. I don't think there's a reason why. I guess people like this picture is why they did it. But
How to work on the overlap, please.
yeah, I think so. And I don't think there's any reason why I wouldn't be able to do that. Okay, so we're doing Gaussian process regression. We have y is equal to f of x plus epsilon, which is noise, and y is a scalar response, and x is a high dimensional feature vector. F is an unknown regression function. So we might think, okay, we can use out of the box high dimensional Gaussian process regression techniques like the ARD kernel. The reason we can't do that, well, what the ARD kernel does is something akin to like lasso, where it does variable selection and then uses the selected features in the regression. But we shouldn't do something like that because in our image example, all of the features are pretty much equivalent. There's not one important feature. They all contain information about the response, and we would like to use as many of them that matter. But it's not meaningful to just select out some of them. So the reason I'm going to keep using the simulation example is because I can draw pictures of it, which are illustrative, I think. But this is 400 training points and then 100 testing points. And P is set to be 10,000. And I just take this 400 by 10,000 matrix and I run that through Gaussian process regression with normal inverse gamma priors, and I can make predictions. So already, this is maybe better than we would think we should be able to get. And this is because of that low dimensional structure in the data, right? It's not just 0 all the way across, but it's not a very good prediction either. So what are we going to do? The rate at which we're able to make good predictions with Gaussian process regression, I ought to have a slide that says this, but I don't have one. The rate at which we're able to make good predictions with Gaussian process regression depends both on the apparent dimension P of the data and on the true manifold inherent dimension D. In the rate, the thing that's up in the exponent that really governs it is the smaller number D. And then on the outside, P shows up and slows things down. So here P is 10,000, and that's messing with our predictions. So our goal is we would be able to make nice, good quality predictions if we could shrink P while keeping D the same. So can we do that? Yes, we can, and we're going to use data sketching to solve this problem. So if you guys were here a couple of weeks ago when Jacob talked, we learned about the Johnson-Lindstrauss lemma, which says that, say we have a set of endpoints, X, right, n by P matrix. And there exists a function which takes us from P down to M, where M is some number that's got to be at least this big that satisfies this. The distance between U and V, where U and V are 2 points in X, is the same as the distance between F of U and F of V. So we have a function that takes us from large P down to small m, but maintains the distance between points. And the distance between points is all that we care about for Gaussian process regression, right? All the action for Gaussian process regression all is in the covariance, which is all about the distance between points.
It's like this distance between the proportion of distances.
Yeah, the relative distances are preserved. I think this 1 over m, sorry. The distances can be preserved, the relative distances are preserved. So the question is, do we have a function f that we know that satisfies these properties? And yes, we have a nice function. If we define f of u to be multiplication by a matrix P, where all of the elements of P are IID white noise, that satisfies the Johnson-Lindstrauss lemma with high probability. So it's a random matrix, so the results occur randomly, right? Go ahead.
So the original data that you presented was an image data.
Mhm.
And that had a lot of covariates, like large dimensions, that's why you want to like.
Yeah, so initially it's size P, right? That's the 4 images stacked into vectors, really big. Image 1, image 2, image 3, all vector, and then just put it into one long vector. I want to project that down to M because I'm able to make good predictions that depend on the inherent dimension D, which is like 10 in the image case, but it gets screwed up by having too high dimensional. So if I can preserve the inherent dimension while projecting down to a lower dimensional space, we're good to go. Go ahead.
M in this case would be like the P.
No, D is something separate. M is the dimension of the space that we're projecting into.
Is that related to P?
I don't know.
New dimension.
I guess it can't be smaller than D, probably.
Yeah.
But M is bounded by this. Sorry, M is bounded by this, so it at least has to be like this big. Like this is like 80 or something, 60 when P is 10,000, I think. So M is just a small dimension. It helps us with the rate at which we're able to make quality predictions. D is some other thing that we don't have access to. We just assume it is small in the data. Go ahead.
The function f of u satisfy that because you want to use that lambda, right?
I just know that it does. I have no intuition for why. That's a good question.
What if, what if you keep epsilon very small, what if m passes the p? I think you don't want that too, right?
Well, I guess I wouldn't do that. Right. I guess I could, but yeah, I mean, the distance between the points is already large, right?
Yeah.
It's in a high dimensional space. So I guess I'm not gonna choose an epsilon that's so small. But yeah, I'll go away and think about your first question and make sure I can answer that. So that's a good question.
This function f equal q, is this the one you are going to assume in your paper?
Yeah.
Okay.
Yeah. So
But also this TIG is distributed as normal. This is a prior.
no, it's we take. So when we actually do it, we're gonna take our data, right? Our original data X, which is N by P, and I'm just gonna multiply it by a random compression matrix. With like this P. And that's gonna be my new data, and I'm gonna run that through Gaussian process regression. So my next slide, oops. Yes, well, my next slide says this, right? We're replacing our original Gaussian process regression model, yi is equal to f of xi. Just take it and plug in p of xi instead. And that preserves the distances, so we're still good to go.
Why do this kind of transformation?
We do the transformation because we need to go down to a lower dimensional space so that so that we're able to make good predictions. So when we do this, this doesn't really change anything with the Gaussian process model. We still assume a Gaussian process prior on F. We place normal inverse gamma priors on the mean and variance. And we're good to go. That's a conjugate setup. So we get normal inverse gamma posteriors. And the question is about prediction. So this we all have in closed form. And then when we move to making prediction at new points, x tildes, the posterior predictive distribution of y new is given to us in closed form. It's a student t distribution with this mean and this variance, where these can all be evaluated. Of course, the usual Gaussian process problems apply. We have to invert these big matrices C, but we know ways of getting around that or speeding that up. But
Before the model is a Gaussian process, so the noise is normally distributed. So after this transformation, it became T distributed.
the noise doesn't become T distributed, but the marginal posterior predictive distribution of Y. The predictions at new points. So like,
Oh, it comes from normal to T.
this is, I guess it's just a result about the normal inverse gamma setup when you marginalize out and you get the,
Suppose the F is T distributed. We can go back to the slide. Oh, here, see the second line F is T distributed.
yes. I might have to check. I don't know if that should be normal or T. I should know this, but
The F is the function, right?
it's the mean function. Yeah. But I know that this one is right for sure. So this is all just standard kind of Bayesian analysis stuff. We integrate, we solve this, we get this one is no in close one.
Intuitively, it's coming out as T because you're having to estimate this covariance.
I would
But that's coming
ask
in-
that you guys just believe that this result is true.
Well, I think it's true.
It is true.
Says that it, you've got this estimated covariance. But again, that's just.
Okay. I don't know.
Maybe Brown's explanation, but.
Anyway, we're able to make predictions at new points Y new. And this is the same example from before. But now we're making predictions where instead of, so P starts at 10,000, multiply it on the outside by a random projection matrix, sketching matrix, take it down to P is like 60, and then run it through the Gaussian process regression. And now our results are better. But because the compression matrix is random, the results are better randomly. We don't know which ones we prefer. Obviously, we like the blue one better than the red one because it makes better predictions, but we're not robust to differences in the random sketching matrices. So we need to find a way that we can become robust to those differences. And the way we're going to do that is by model averaging. We're going to average over many random sketching matrices. The only difference between these two is that I've taken different random sketching matrices. So I compress both of these from P is equal to 10,000 down to P is equal to like 80 or 60 by multiplication by just white noise matrices. But those are two matrices that are sampled differently. So the results are dependent on those sketching matrices.
But there's no, like, no standard way of choosing a good.
Yeah, we can't choose a good one. We can just generate a bunch of them and just evaluate everything because we don't have to do any expensive sampling. Okay, so we need to do model averaging, right? We're going to average over K many different random sketching matrices. So the predictions, like I've said, are dependent on the sketching matrix P and on the parameters in the Bayesian model. And in order to lessen dependence on any single random model, we're going to average over K of them. Previous work used Bayesian model averaging, but I'm going to argue that this is not a satisfactory way to go about model averaging. And instead, we're going to use stacking of predictive distributions, which is a technique that people know about, and I should have a citation. So in the model averaging setting, say you have your model list of MathCal M, and that contains your K many models. The model list falls into one of three relationships with the true model. So the M closed case, the true data generating model, is contained within the model list M. M complete and M open are kind of similar, but I guess philosophically different. M complete says the model exists, but it's not in M, but I guess we can write it down. And M open is, we don't know what the true model is, but we also don't specify that it's not in the model list. So Bayesian model averaging is appropriate in the M closed case. It's going to select the true model. But in the incomplete and M open cases, what Bayesian model averaging does asymptotically is select the closest model to the true model that's contained in the model list, which is not what we want to do. We don't want to just select any one of our models because they're all equally nonsense. We want to average over many of them.
The typo is an issue with PMA.
Yes.
But it looks like it's not an issue, it's a reason.
There is an issue. Well, there is an issue because the issue with Bayesian model averaging is that in the end, it's going to select one of these two. Right, all of our models in the model list are these random compression matrices and then the associated hyperparameters. So all of our models are kind of nonsense. All we care about is making predictions. Bayesian model averaging asymptotically is going to select this one or this one, but we would like to try and put these together to make better predictions. Do you see the? So that's our issue with Bayesian model averaging. We don't want to select one model because we know none of our models are correct. We want to select the sum of all of our models that gives us the best predictions.
You select some of your models, or you want to select some of the, like a mix.
Yep.
A new model.
Yep.
Or is it-
So instead, we're going to do stacking of predictive distributions, which I'm gonna give a little background on. So, okay, like I've said, we need an averaging method which privileges the predictive performance of the models. We don't care about whether or not they're true because we know they're not. So scoring rules give us kind of a loss function that allows us to do this. Scoring rules assess the quality of probabilistic forecasts by assigning a numerical score based on the predictive distribution and on the event or value that materialized. So we can compare our predictions that we make with the actual true results. And these let us score different probabilistic models. Since we know the posterior predictive distribution of y tilde new points, we can efficiently evaluate whatever proper scoring function that we choose and use this as a loss to average our weights for adding together our models. So originally there's a method called stacking. You start with your data, yi, xi, and parametric models nk that have some form f of k is equal to x and your parameters. And you fit each model to the data and you obtain leave one out predictors at each data point. So at xi, I'm going to predict xi given the rest x minus I. And then I'm going to take all of those n many leave one out predictions and solve this optimization function for these weights, which minimize the difference between the true observation yi and our predictions at the I many leave one out. And I'm going to solve for these weights, which minimize this, and those then tell us how to add together our predictions at new points. So this is stacking. This is for regular old statistical models.
I said, optimization in programming, what kind of, like that, is it like R
Yes.
code or Python code, how do you do that?
I use there's a constrained optimization package in R, and then I use the BFGS optimizer. But you have like there's an additional constraint that the W sum to 1, so it becomes kind of a painful optimization problem. Go ahead.
So for each model, is there an equal weight? Like, does each model?
No, no. The goal is to find the weights for each of the models
Okay.
that sum together and give us the closest to the truth. Right. So if you have a model that's really bad, hopefully you give it not very much weight. If a model is not very good at making predictions, hopefully you don't give it much weight, and you won't under this loss. But we don't just have the mean, we have the whole posterior predictive distribution. So we can repeat the stacking process above, but instead of solving with the squared error loss, we're going to use a proper scoring rule for our predictions under our probabilistic models. So instead of just evaluating the likelihoods at each of the left out points, we instead obtain the predictive densities for each model at the left out points. And again, this is a t-distribution that we can just evaluate. And then we solve this optimization problem. So instead of doing the squared error loss, we're gonna use the log score. And now we have to find the maximum. We're gonna maximize the score of the over these weights in the simplex of the posterior predictive distribution at yi. So the higher the likelihood pk minus I at yi is, the more we like, right? The more it agrees with the truth. So then, just like in the last step in the stacking, the final posterior predictive distribution is given by a weighted average of the other previous posterior predictive distributions over the different models. So these are notes from before. Instead of, ignore the first one, instead of leave one out, right? You still have to, in Gaussian process regression, you still have to invert the covariance matrix. And with leave one out, you're gonna have to do n inversions of n-1 times n-1 covariance matrices. So that's a problem. So instead of doing that, you can do, you can split the data into k folds, or see, k folds is not good, but something else, not the number of models. So if I set it to 10 folds, that speeds up computation and that gives pretty much equivalent performance. And then solving for the weights is, like I said, using BFGS optimizer. And in the original stacking of predictive distributions paper, they also wrote a package and they have nice code for doing this. So here we are back to our original example. I have the blue model and the red model from before, and I solve the stacking problem and I get my new predictions, which are the purple ones, and it's better than both of them. Right? You can see that it's going in between and it gives nicer performance.
The stacking model is like, is it cheap to evaluate because?
Yeah, so we're able to do this, right? So the stacking requires that I evaluate that predictive density at all of the leave one out points, right? If I had to do some kind of sampling to evaluate that density, this would not be great. It would take a long time. Right now, you don't have to do any sampling. It's just available in closed form, but the bottleneck is the size of the covariance matrix. So it's the normal Gaussian process bottleneck that we're dealing with, but I can just evaluate it every time. So, okay, if we jump up from 2 models to 30 models, 30 stacked random compression matrices, we get much nicer results. And this 0.366 is way better than anything we were seeing before. Okay, so here's my picture for putting it all together. You have your original data X, which is n by P. And then you take the data and you multiply it by K many projection matrices. P, which take you from n by P to n by M. And then you evaluate Gaussian process regression, right? You can get the posterior predictive distribution of Y new given Y and the models. And then you stack those together and you obtain your final predictions. So that's really the whole thing of the method. Now I can get into results, but I'm also happy to take any questions. Go ahead.
The theta and the
Yes.
size of our hyper.
Yeah, these are hyperparameters in the. They are, let me find them. They're here. They're hyperparameters. Theta is the, there it is. It's the length scale in the covariance. And psi is a signal to noise ratio.
Did you just kind of choose those in kind of standard ways, like how most people would?
I evaluate them over a grid. I have a slide at the back, but because everything is, again, so the real power of this whole method is that we're using this conjugate prior setup. Everything can just be evaluated. So I can just evaluate these things, fixing those hyperparameters on a 2-dimensional grid, and I can find ones that maximize the likelihood.
How sensitive is the model for like, depending on how small of a, like a projected?
That's a good question. I have a slide. All right, this is my favorite slide in the whole thing. So this is, I think, the coolest plot I made. So sketching dimension is M, projection into whatever dimension. And then here's the mean square predicted error for just that Swiss roll model. As M increases, right, we get worse on average. I think these are too small, like these are actually breaking the rules on what M is allowed to be. But there's kind of a sweet spot where it doesn't matter that much. As long as M projects down to a small enough size, we're good to go. But what I think is really cool is that this shows that sometimes you're still able to make good predictions with Gaussian process regression, even if you're not doing any sketching at all, right? We're taking this, we have 5,000 dimensions. It's just the variance in our predictions is much larger, but you're still able to make sometimes high quality predictions. But I thought, when I realized that, I thought that was really cool, but we're kind of robust to changes in M, as long as M is large enough, but not too large. So my results, I compared my sketched Gaussian process method to some other like tree-based methods and Gaussian process methods and a neural network. Just kind of a simple whatever, multi-layer neural network, nothing crazy. And we won, so that's good. And we have smaller variance, so also that's good. We mostly won, not always, but also I compared the length of the predictive intervals between my method and these competitors, and we're making better predictions while also maintaining smaller predictive intervals on average. Oops. I also have runtime analysis, so kind of, it's not totally fair how I've compared them. One is I'm changing the number of features, and another one while keeping the sketching dimension fixed, and the other one is I'm changing the sketching dimension while keeping the number of features fixed. And of course, things like where I don't do any sketching, like random forest or BART here, they just increase linearly with the number of features, whereas the sketch things stay the same. And as I can increase the sketching dimension, right, whatever. But the good news is that my method's very fast, even on pretty large data sets. Not once you get to be too large, but still it's pretty good. This is the plot I showed about M. Now, back to the real data example that I started with. We have satellite images over Las Vegas, and we have the daily monitor readings. This is July 2nd, 2019. Here's the original image in the near infrared band. And then on the right, I do some screening. I just do a non-parametric independent screening approach. Our famous speaker from last week, it's one of his methods, so I cited him like Dr. Harris said I would. And this is the screen results. So some of these don't change that much over time, but this is the data that we actually plug into the method. And when I run it through the method, here is the quality of predictions I'm able to make. So we're still able to make good Gaussian process Gaussian process regression predictions, even with this complicated image data. That's the takeaway. In creating this, I sampled out every third data point is held out for a prediction. I couldn't remember which one. So I use every third data point, that's the test set. So clearly there's some problems. I'm not treating this correctly as a time series problem. I'm doing my best to construct IID data out of this varying temporal thing. Next steps are taking the temporal aspect into account. But here we go. We beat the other methods, as you would expect. And the takeaway is that we've created a Gaussian process regression framework that draws predictive inference from a random variable from a high dimensional feature space using sketching of the feature vector down to a low dimension. Our method's really fast, doesn't require any MCMC, and the way I set it up, it's already parallel. It's scalable. Something I'm currently working on is scaling this up to large N by just replacing the inversion of the covariance matrix with the sparse Cholesky vector setups like Gailliot approximation, and we naturally quantify uncertainty. So I think it's quite a nice method. But all right, that's it. They do on time.
And go back, please go back to the models you compared with the
Yes.
other methodology.
Here we go. So I just compared with some tree-based methods like random forest and BART. I compared against regular Gaussian process regression, and then I compared with a like a fully connected multi-layer.
There is neural network, what kind of neural network?
Just a regular like multi-layer perceptron. I didn't do anything too fancy. I think clearly I should compare with something like a convolutional neural network or something. I think we're going to run into problems because there's not really that much data. Here I only have, I don't know, like 1,500 days, something like this. But yeah, I just compared with some easy to implement out of the box.
Tuning the neural network is really a topic.
Yeah.
How do you know if you are tuning the tree is optimal? You don't care?
I do care. I just used whatever the Atom optimizer stuff that I can do out of the box in Python. So I read what kind of the best practices are. I followed those, but I don't think that the neural network I attempted here, I don't think it's well designed for handling this kind of problem, right? But I think there are other types of neural networks that would be better to use, but I find them all to be pretty complicated and ran into some trouble using them.
Have you tried any time series models?
Time series models work great for predicting this kind of shape. I tried things like, so here I'm just, we're learning the mean, right? Well, maybe I don't want to learn the mean. I want to remove the mean and I want to learn the noise. And I fit some kind of AR model to it. Works perfectly. So time series models are great, but they don't solve the problem of I'm trying to predict the air quality given the image data. So if I just have the air quality readings over time and I apply a time series model, there's no problem. But it's not solving the problem that I'm trying to solve.
But one thing I was wondering is, so what's the practical motivation for using the images to get the air quality?
The practical, well,
Why use the images? Why not like constructing? Are they kind of
so there's air quality monitors are expensive and they only collect sparse data, like spatially, right? So my example is only in Las Vegas, right? But if you've seen, there's been a couple talks in the department, like Cheng Wu gave a talk about using air quality monitors in Houston, right? And he showed that there's like 6 air quality monitors in Houston, and then he interpolates this map.
Yeah.
The idea is if we can define this like regression relationship between air quality and satellite images, then in principle, we could kind of do a map of the whole US. We could just use the satellite images to predict air quality wherever we look.
you do that by using this method, training it on the known data? And then
Yep, that's our hope. That's our next. I'm working on stuff to scale it up to high dimensions so that I can go and beg for more data. But yeah. So that's the dream, like that's the goal.
Because we already have satellites in the
Oops.
thing, right? It's easier to collect that rather than trace out these monitors.
Yeah, so this is a good question from Abhishek. So the weights kind of, a lot of them are 0. And then a lot of them are small. So it tends to do just kind of an averaging, like I should show a distribution of them. That's a really good question. But this kind of thing where the weights are, 0.4 and 0.5 is a pretty common thing. Did you guys get the question I was answering? Sorry. Okay. But yeah, I should show a histogram of those. That's a good idea. Go ahead, Dan.
So really nice talk. And
Thank you.
that's I would be just curious if you look at it as something really like nice, like principal components regression, right? The
Mhm.
idea is kind of the same.
Yeah.
You're reducing your dimensionality, and I think you're more sophisticated and would work better. But I just want to, I would be curious to see like what the game is.
Yeah, I will do that. That's a great idea. Go ahead, go ahead. Nowhere. Right now, I submitted it, so it's submitted, but I haven't uploaded it on archive yet. I can send you the paper. I'd be happy to do that. But no, I haven't uploaded it yet.
All right, thank you very much again.